topic for you, one of the most mysterious objects in the universe, and that is black holes. How are you doing, Rachel?
Well, thank you.
Yeah, all week we've been delving into black holes. We've got activities. Hopefully, everyone here joining us in the chat has checked out our weekly videos that we're doing with Let's Talk Science with Morgan. You can check those out on our YouTube page. There's a really fun activity if you want to learn about the expansion of stars, because there is sort of twofold kind of like understanding. And Rachel, you're gonna kind of talk about the beginning of kind of like, how do we get the black holes? But before we kind of talk about how we get the black holes, we have to talk about stars. So that's going to be the first half of the presentation, and then we're going to get into black holes. So I am super excited to get going. For all of you out there watching us, we're going to get to all of your questions. That's going to be like the second half of our half hour today. So please comment in the chat. Please be respectful, of course. And we will try to get to everyone's questions. We'll obviously tackle all of the life cycle of stars questions and black holes questions first, and then if we run over those, so we'll get into any questions that you have about the universe. So without further delay, let's hand things over to Rachel for our presentation on life cycle of stars and black holes.
Perfect. Thank you, Michael. So I'm just waiting for my screen to start sharing. So like Michael said, I'm going to walk us through the life cycle and evolution of stars, starting from the baby star all the way through the weird, awkward adolescent teen years and all the way through to the end. So we're starting here at planet Earth, where we're actually going to jump to a nearby nebula. So stars are born in stellar nurseries called nebulae, and they're basically these giant clouds of interstellar gas and dust, much like this one, which is the Orion Nebula. Now, the ultimate fate of a star is determined by its initial mass, assuming that it doesn't gain mass through other events like mergers. Now, around 4.5 billion years ago, waves of energy traveling through space pressed these clouds of gas and dust closer and closer together until gravity caused them to collapse in on themselves and start to spin around and around. Now, as the gas starts to spin faster and faster, it starts to heat up and eventually flatten. And it'll eventually gather enough mass in the center to form a baby star, or what astronomers call a protostar. Now here is our sun at its birth. You can see it right in the center as a tiny, tiny white dot. Now, it started out as a ball of hydrogen and helium that is not yet powered by nuclear fusion. And we also see the hypothetical orbits shown here in blue of the planets. And I say hypothetical because remember that the planets haven't quite formed just yet. And the hypothetical planet lines will give us a sense of scale as our sun starts to evolve through the different phases of its lifetime. Now, eventually, over the course of millions of years, the temperature got hot enough inside the protostar to start the process of nuclear fusion in the cloud's center. This is our sun now. Now, the star will burn hydrogen in the fusion process until its fuel runs out. Now, the star is in a delicate balance between the outward pressure from nuclear fusion and the inward pull from gravity. Now, eventually, when the hydrogen supply in the core runs out, the star can no longer generate heat and pressure through nuclear fusion, and the core becomes unstable and contracts. The outer shell of the star, which is still mostly hydrogen, starts to expand. And as it expands, it begins to cool and glow red, just as you're seeing right now. We call this the red giant phase because it's red and it looks gigantic. Now, our own sun will reach this phase in about 5 billion years, expanding all the way out to just about the orbit of Mars. Now, after the outer layers have expanded, over the next few tens of thousands of years, the star will eventually radiate away this outer layer through solar winds. Stars around the mass of our sun will eventually leave behind a much smaller, dense core, and that's called a white dwarf. And you can see it right in the center here. Now, white dwarfs are no longer undergoing nuclear fusion, so they'll start cooling over a long period of time. Now let's ask what happens to more massive stars. Well, after the red giant phase, they'll undergo something called a fast core collapse. Now the inward pressure of all that collapsing material is so great that a huge rebound explosion happens, and the star's material, all those heavy elements, are spewed out into space in a violent explosion. And it looks a little something like that big white flash of light that you just saw. Now, what's left behind after a supernova? Well, it really depends on how heavy or how much stuff you had in the beginning. If you had around 8 times the mass of our sun, you'll leave behind something called a neutron star. Now, neutron stars are these extremely dense objects that are about 10 kilometers across. So that's around the size of the UBC Vancouver campus. Now, it could have the mass of 3 suns squished inside the size of UBC Vancouver. And these are the densest objects in our universe. Now, sometimes as the white dwarf collapses to form a neutron star, it gains a lot of spin in the process, and you end up with a rapidly rotating neutron star, or what we call a pulsar. Now, pulsars are highly magnetized, which means that beams of radiation flow out or pour out along the poles and along these magnetic field lines. Now, researchers study pulsars by looking for these pulsing beams of radiation from Earth. Now, what happens if our star is much, much, much more massive than our sun? Let's say anywhere between 15 to 20 or even more times the mass of our sun. Then after its white dwarf stage, it'll form a black hole. Now, by packing a lot of matter into a very small volume, the result is a gravitational field so strong that nothing can escape, including the fastest thing in the universe, which is light. Now, a black hole's gravity is strong enough that it can actually bend light rays that pass close by. And let me show you what I mean. We call this effect gravitational lensing, and you can kind of see the light being bent around this black hole. Now, black holes aren't the only objects that can lens light. Any object with an extremely large mass can bend light, and sometimes it can even form a ring of light around the object, and that's called an Einstein ring. And here's an example of one. Looks a little something like this. This is an Einstein ring. Now, the effect of lensing is like looking through a gigantic magnifying glass. It allows researchers to study the details of early galaxies that are too far away to be seen with current technology and telescopes. Now, the gravitational strength of black holes is so strong that it can actually also warp the fabric of space-time. We saw this during a gravity-themed week where I talked about gravitational waves, these ripples in the fabric of space-time caused by 2 massive objects orbiting each other. In this case, we're watching the merger of 2 massive black holes, or what we call binary black holes. Now, we learned that matter tells space-time how to curve, and space-time tells matter how to move. And this is a great example of matter telling space-time how to curve, or how to warp, with these ripples that are propagating through space-time. Now, I'm going to switch gears a little bit. I'm going to switch to a PowerPoint just to talk a little bit about the anatomy of black holes, because a common question that I get is what would happen if I fell into a black hole? Well, let's first get familiar with the terminology. And let's use a whirlpool as an analogy for a black hole and a boat for our observer. Now, we have the event horizon shown here by this line, this circle that goes all the way around, which is the boundary of no return. So if we pass beyond the event horizon closer to the singularity or the center of the black hole, we see that space is being pulled faster than the speed of light, which means that it's actually impossible to escape a black hole's grasp once you've passed this threshold, because we know that nothing can travel faster than the speed of light. Now, I preface this a little bit, but at the heart of a black hole is a gravitational singularity. It's this one-dimensional point containing a huge amount of matter in an infinitesimally small point. And here at the singularity, density and gravity become infinite, and space-time actually curves infinitely, and the laws of physics as we know them stop working. Okay, so now we have a little bit more background knowledge on black holes. So let's watch a short video on what a simulated view of falling into a black hole would look like. And it's really cool. So we have a clock on the right-hand side, which records the time left until you hit that inner horizon. And we also show here the orbits. In the green zone, we have the region of stable circular orbits where you can orbit around the black hole safely. The yellow is unstable circular orbits. In the orange and red part, we start to get closer and closer to the horizon. And here, we're just about to cross the boundary of the event horizon. So what's really cool is that for a while, you'll notice that the black hole starts to increase in size. It looks like we're going towards it. But then you'll see that the black hole actually starts to shrink. So it looks like we're approaching the inner horizon. It stops expanding and then it starts to shrink. And it looks like you're kind of moving away from the black hole. And we're not actually moving away from the black hole. So this is the part where it's getting bigger and expanding. And we'll see it start to look like it's going further away. So we're not actually moving further away. We're still going towards that gravitational singularity at the center. But this effect where it looks like we're moving further away is something called relativistic beaming, which is where you have all of what you're seeing, all of that light concentrated to in front of you. So here we are. It looks like we're backing away from that center of the gravitational singularity. And there we have it. So that is kind of what you would see if you were to pass through a black hole. Unfortunately, we can't do that without getting turned into spaghetti. But I think it's cool that we're able to simulate what it just might look like through black holes like that.
Awesome, Rachel. Well, last night we had a wonderful event with Natalie Roulette back over at the University of Montreal. We learned lots about black holes, but of course, for anyone out there on YouTube, if you have any questions about the life cycle of stars, about black holes, put them into the chat because we're going to get into them. And maybe, Rachel, let's start with some of like the fun stuff that we talked about last night. One of them, of course, is what happens when you go through a black hole. Like, what's on the other side of the black hole? What are sort of like your thoughts around this?
That's a great question because this is where my imagination tends to run a little bit more rampant rather than sticking to the science, because we don't really know what's beyond a black hole, right? It's impossible to send someone in there. I don't think anyone would like to volunteer to go into a black hole. But, you know, we do have these ideas that come from both theory, mathematical equations, and also from sci-fi. We have this idea that maybe we could have wormholes, so a portal to another universe, another dimension. We also have the idea that maybe there could be this hypothetical thing called a white hole, which is essentially the reverse of a black hole, does all the opposite things. And I think that, you know, I'm really hoping that we'll be able to figure out exactly what's inside a black hole. But for now, we'll have to make do with what Interstellar tells us is on the other side.
Which is a bookcase?
Yeah, a bookcase, or I think they had a tesseract, which is an interesting concept because, you know, there's this idea that a tesseract, and if you shine a light down on a tesseract, the shadow is really another dimension that would be like the temporal or time dimension, and it gets a little wonky from there.
That was certainly the more optimistic view because when I was watching movies about black holes, there was two that come to mind. There was Disney the Black Hole, which apparently there's hell. But then that was explored even more in the horror movie Event Horizon, which came out in the 90s, which is, it's a cool movie. It's very scary, though. I don't know if any kids out there should be watching that, but lots of really cool theories. One question that did come through from Evendro, which you did sort of talk about, Rachel, is what happens when two black holes merge or collide together. And of course, we did see that when we saw the gravitational waves. But one thing that I found really interesting is talking about, you know, there are different sizes of black holes. So what are we really talking about? What's going to happen if two supermassive black holes merge together?
That's a good question. So it's kind of a hard concept because when we think of black holes, and even when we think of ultra dense stars like neutron stars, we're thinking of this spherical object that does have this boundary. But when we're talking about black holes, this boundary is more so not a physical boundary, but more so this boundary that tells us that if you're traveling at the fastest possible speed that you can, at the speed of light, you actually can't escape. So it's kind of hard to wrap your mind around the fact that it's not a physical boundary. So when you're looking at two binary black holes that are orbiting each other, getting ready to merge, they'll orbit each other faster and faster because their gravity is affecting each other. And so we get these gravitational waves, that all this energy is spewing off from these merging black holes. And eventually, after a process called the ring down, where they orbit each other very, very quickly and end up merging together, they become one supermassive, ultra heavy black hole.
Now, you know, a question that I have about that is, so of course we felt the effects of those black holes that collided through the gravitational waves. But of course, what we're talking about is very minuscule. You know, it's not affecting us in any way. But are those waves, are they depleting in strength? You know, kind of like when you drop a pebble in a pond, you know, the ripple is strongest closest to where that event happens, but then it eventually gets weaker and weaker. So if two supermassive black holes collided, would sort of like the surrounding area, would the gravitational waves, would they be really strong that would affect the planet and be dangerous for people if they were living there?
Right. So two things to keep in mind for that is one, that these gravitational waves, these ripples in the fabric of space-time, are propagating at the speed of light. So they're actually traveling very, very quickly. And the only thing that we have to keep in mind when thinking about as these waves are traveling through space is that space is itself is expanding. We get more space in between the space that we already have. So we have this idea that's called redshift, which is essentially, for example, when you're looking at black holes, the light that you get from them is actually being redshifted towards the longer frequencies. So in visible light, they would get shifted towards the red because red has longer wavelengths than the opposite side, let's say violet. And so they get shifted and shifted until they get so stretched out so long that they start getting into the invisible wavelengths. So there is this effect that we have to keep in mind, but they do travel at the speed of light, and they are extremely energetic to be able to travel, you know, millions or billions of light years across the universe to reach us.
Right. Maybe just for people that maybe don't know what redshift and blueshift means, maybe just quickly describe what that is.
Sure. So it's really this effect of when us on Earth, we're trying to look at an object in space, and that object is moving relative to us. So it's either coming towards us or it's moving away. So you can imagine kind of like if you've ever sat on the side of the road and heard an ambulance go by. As an ambulance,
may go past very soon, actually.
Well, there you go. That's a really good example of this idea of redshift. Really, that's the Doppler effect, but it's kind of the same thing where you have the source that's emitting some sort of waves. As it's going towards you, it's still emitting. So the spaces in between those wavefronts get shorter and shorter. So your pitch actually goes higher and higher. But then as that ambulance passes by you, it starts driving further and further away. It's still emitting, but because it's driving away, the spaces in between those wavefronts get longer and longer. And so that's kind of the idea of blue shift when it's driving away and red shift when it's coming closer. Mm-hmm. Or rather the opposite. Red shift when it's driving away, blue shift when it's getting closer, because bluer has higher frequencies.
Right. It's like the...
Exactly. That was perfect.
That was my best ambulance impression. Another question coming in from YouTube. So what is this, talking about speed, what is the connection between warp speed and black holes? And, there is, Star Trek logic, there's sci-fi logic, and in a lot of those, there is, some scientific plausibility around, bending space in order to achieve sort of like this warp speed. Do you have any thoughts on elaborating on warp speed and maybe black holes and how it's connected?
Yeah, so they're a little bit loosely connected, but they're connected under this umbrella idea of faster than light travel. So there is that idea from Interstellar where you could have a wormhole that connects two very distant points in spacetime by just bending the fabric of spacetime itself to bring those points right on top of each other. So that's an idea of faster than light travel where you can just skip all of the space-time in between and get from point A to point B very, very quickly. Now, the idea of warp speed or warp drive is this idea that you can almost ride space-time like a surfer on the crest of a wave. And how you would do that is you would have to deform space-time faster than the speed of light to create that wave, almost like you're trying to like in a wave pool where they push the waves and you can kind of ride the crest of the wave along the wave pool. It's kind of the same idea where that wave can carry you faster than the speed of light as you're traveling at the crest. It's a crazy idea.
It is wild. And of course, like that's really kind of like the core idea in a lot of science fiction, because if you don't have warp speed or warp drive, you're really relegated to our solar system, right? Like humans are not going to be, going on trips, to other solar systems. It's just not feasible. So, I always wonder that, is this something that is kind of like it's it's that barrier to kind of like to all of the ideas in sci-fi. And if we don't achieve this warp speed, can we just forget about all that? Like forget about ever coming close to even looking at a black hole up close, because we'll never be able to get close, right?
Yeah.
And are we always going to be confined to our solar system? These are sort of like the thoughts that I have. Is that sort of like a stumbling block in science?
I really do think that the limitations of space travel are they really come from the limitations of the human body itself. So
Yeah.
if we're able to put the body into maybe like a deep sleep as we're traveling, however many years out into deep space, maybe that would be a solution. But like humanity has proven us time and time again that we do surprise ourselves with the technology and the rate at which we're advancing that technology. So I do think that we would get that technology, just whether or not our bodies could handle it is really the main question.
Yeah. Another really interesting question here. So first off, Rachel, have you seen Disney's The Black Hole?
I have not, and I was very surprised when you told me yesterday that but Beyond the Black Hole was hell. That didn't feel very kid friendly for Disney.
It was. I'll tell you a story about this movie. Is that just like Star Wars? When I was growing up, we didn't have VCRs until a little bit later on. So like in the early '80s, I might have seen a film in the theater, but the only other connection I had to it were like these picture books. And I remember having the Black Hole picture book, and I then watched the film in my adult life, and I realized I don't think I ever saw this film, because in the picture book it is a very PG version. Like there's no violence, there's cute robots, but there's some really scary robots, and there's some really hard sci-fi ideas in the film. So one of the questions that came out on the chat here was, if you were to be a science advisor on the black hole, would you do it? And what sort of recommendations would you make? So just give you a little synopsis of the film. There is a spaceship that's kind of parked on the edge of a black hole, and they have figured out a way to safely navigate through the black hole. That's the basic premise. There's a bunch of other wild concepts going on, but that's the basic premise.
Okay, so the answer to the first question, would I love to do this? I absolutely would. That it would be such a dream, because for people like Kip Thorne, who was a theoretical physicist who was an advisor to Interstellar, doing all those calculations and running the simulations and actually seeing visually that output rather than just numbers scribbled on a page is very satisfying and very rewarding. And it helps with public awareness, because with that film, they did try to get as close as possible or as accurate as possible as they could with a little bit of artistic license. If I was going to remake Disney's The Black Hole, I think I would probably go the wormhole route out into a white hole and maybe pop out in another dimension. I feel like that would be a really radical idea that kind of like when Einstein first came up with black holes, also thought was a radical idea, ended up 100 years later that it was true. And I feel like wormholes and white holes are maybe on that same level of seems bizarre now, but could be very much from sci-fi to science fact.
Right.
Yeah.
Well, I mean, it could happen. I mean, there's a Disney Plus now, and they're looking for all sorts of content these days. So you very well could see it. And that could be an opportunity for you, Rachel. We don't want you to leave us, but
maybe part-time.
Another question coming in. If black holes absorb energy and energy cannot be created nor destroyed, what happens to all of that energy that goes into the black hole? That's a really good question.
Oh, yeah. So there is this idea that once things go into the black hole, they never can escape. They can never leave. But then Stephen Hawking, and I believe 1974, I want to say, came up with this idea of Hawking radiation, this idea that black holes actually do radiate something. And it's a really cool idea because this told us that black holes actually are not eternal. They don't live forever and forever. They can actually radiate away and actually shrink and eventually dissipate and dissolve away. And it was kind of this cool idea because, Hawking showed theoretically that the smaller you are, a micro black hole, the smaller you are, the faster you actually radiate away. And the larger you are, the longer it takes. So I think that that's a really cool idea, that black holes actually do emit something, rather than, swallowing up everything.
Yeah, and that's a really interesting point you make, because there are these jets that get jettisoned out of black holes, right?
Yes.
And I actually just learned this term blazars, which is a really cool word to say. But there are these jets that are like that emit, all of these this matter almost at the speed of light. Like this, these are crazy objects.
Yeah, and it's cool that mentioned blazars, actually, because that was the object that I researched in my undergraduate lab course. I actually picked. I thought that also had the same reaction as you, that blazars. I'd never heard this name before.
Yeah.
They have a more formal and boring name that are called BL-LAC objects, but I thought blazars, oh, that's so cool. They're these really highly relativistic, super energetic, have these beams of radiation, and are highly variable. So their brightness varies a lot over short time scales. And they're very interesting objects.
Yeah, and you know what? I was just watching a bunch of videos about blazars, and there was this one really cool TED Talk actually by this astrophysicist Jedidah Eisler, which I highly recommend people going out and watching, because she's an astrophysicist at Dartmouth, and blazars are this new term that I just found out about. Maybe if I can find the TED Talk video, I'll put it into the chat so people can watch it. It is really cool stuff. All right, so we're almost out of time. We've got about 4 more minutes. We do have another question that I did see come in here, which did come up last night, which is, if we go back in time to when the first stars were just being formed, what would have come first? Black holes, or so we didn't have black holes in the early universe, right? Because we didn't have stars that were massive enough. So at what point, in the universe did we start to have black holes?
That's a great question. There's this idea that we actually could have these things called primordial black holes, and they would be these black holes that didn't form from stellar collapse, or what we would call astrophysical black holes, that are from, like, they've gone through the whole evolution of the life cycle of stars, had enough mass to end up as a black hole. And the idea behind these primordial black holes is that they existed right after the Big Bang. And that's because the Big Bang had this really, really highly fluctuating, super dense regions that were fluctuating. And there's theorized that in these regions, they could have some parts in these fluctuations that happen to have enough matter packed into a small area to form these micro mini black holes. Because really, we're thinking that black holes are just a bunch of matter packed into a really small area. So this interesting idea to think about, that we could have black holes that didn't come from stars and actually were from these very, extremely dense fluctuations at the beginning of our universe.
Oh wow, that's amazing.
Interesting concept.
So are there studies around looking for some of these mini black holes?
Yeah, so it's a little bit difficult because, we're talking about right after the Big Bang. So the look back time on that is, like the 13 some billion years into the past. So we have upcoming space telescopes. Of course, James Webb is coming up, helping us to look further back in time than Hubble is, but we're still not quite at that point where we can look right after the Big Bang and see all these density fluctuations happening, and perhaps even seeing these primordial black holes forming.
Yeah, and it's funny that you mentioned about some of the new technology. So James Webb Telescope is going to be coming out. That's going to help. But there is a telescope right now that is taking pictures of black holes, and it's called the Event Horizon Telescope. And you probably saw this picture come out last year, and that was the first ever actual photograph of a black hole. And that was of a black hole in another galaxy, M87. And what's really neat is that this telescope, which is actually a combination of a bunch of telescopes all around the Earth, is taking a picture of our black hole inside of our Milky Way. It's a really cool project that I sat down with Daryl Haggard from McGill University in Montreal, and she talked about working on the Event Horizon Telescope. I recorded an interview with her, and we're going to put that interview in the chat because we're almost all out of time today. Thank you so much to everyone that joined us today for our weekly chat. Of course, if you'd like to donate to us, you can go onto our website and donate now. Next week, we are going to shift gears back to Earth, and we are going to be talking about another very challenging subject: how tides work. And Rachel is going to be talking about it, from obviously the space point of view, but we have a very special guest coming to us from the Vancouver Aquarium, Catherine Poe, who's going to tell us a little bit more sort of how the oceans work. So that's going to be a really fun talk. Hope to see everyone back next week at 2 o'clock, same time. See you then.